Hello everybody, I'm Madhura Kumaraswamy, a PhD student from the Technical University of Munich, and today I will be presenting a research paper titled Exploiting Dynamism in HPC Applications to Optimize Energy Efficiency. As more and more transistors are being crammed together to satisfy the increasing need for computational performance, there is an increase in a system's energy consumption, which in turn is a major driver for the total cost of ownership of HPC systems. Scaling current systems to reach the exascale level would require more than 50 megawatts of power. Thus, the challenges related to power and energy consumption are a roadblock in achieving this milestone. Soon, users will be forced to optimize their code with respect to energy efficiency or power. HPC applications typically exhibit changing characteristics known as application dynamism in different regions of the program, where the program execution may jump between compute, memory, and IO-bound code regions due to changes either in the workload at runtime, in the control flow, or the execution of different algorithms. Dynamism can be found in many current HPC applications. One such example is a sheet metal forming simulation called Indeed. The figure illustrates the trend of the execution time across the individual time steps of the main progress loop. These time steps are called phases. Indeed is a highly dynamic application and performs an adaptive mesh refinement when different tools come in contact with the workpiece. An application may exhibit interphase dynamism from changes in the execution characteristics due to changing control flow while the simulation is progressing through the sequence of phases. In addition, the application may also exhibit intraphase dynamism either due to data-dependent variation in the characteristics of a region over time, such as in grid refinement or due to different invocations of the code regions. These runtime invocations are called runtime situations or RTSs. Thus, we can exploit the variation in the characteristics between individual phases for tuning. However, detecting this dynamism manually is a time-consuming and painstaking task that demands severe programming effort and domain-level expertise. One solution is auto-tuning. Setting a single frequency for the entire application run is suboptimal due to changing computational characteristics. Instead, individual phases can be grouped by characterizing their behavior using metrics of features. This enables us to select different optimal configuration for each group of phases. In this paper, we expand on the work done in the EU Horizon 2020 REDEX project and present a plug-in-based auto-tuning approach to dynamically switch hardware parameters such as CPU and uncore frequency and system software tuning parameters such as number of OpenMP threads at runtime. The two-stage methodology consists of the design time analysis and the runtime tuning stages. Scopy is used as a common instrumentation and measurement infrastructure. The tuning methodology begins with a series of pre-analysis steps to determine if tuning the application potentially results in energy savings. All fine granular regions are filtered using the Scopy auto-filter tool to prevent measurement overhead. Then, the REDEX Dyn Detect tool detects dynamism by selecting different significant regions that are coarse granular. It also computes the tuning potential by quantifying the application dynamism with respect to the variation in the execution time as well as the compute intensity. It ends up detecting intra and interface dynamism and outputs the list of regions into a configuration file which is read during design time analysis. Design time analysis is performed by the Periscope tuning framework, which calls tuning plugins that perform experiments using a specific search algorithm to evaluate the effect of system configurations on the application execution. At the end of the design time analysis, the tuning plugin generates a tuning model consisting of the best configurations for both the phases as well as the RTSs. This tuning model then drives the runtime tuning stage, which is performed by the REDEX runtime library. The interface tuning plugin tunes the interface dynamism of an application. It performs 4 different tuning steps. In the first tuning step, the plugin evaluates a single phase of the application in each experiment. It reads the significant regions, the ranges of the tuning parameters, the number of experiments to perform, as well as the objective function. For our evaluation, we selected the normalized energy as the objective. The collected values of the objectives are used to compute the savings in the final tuning step. In the second tuning step, which is the cluster analysis step, we select different features in order to characterize the behavior of the application. The process of determining the best system configurations can be done using an exhaustive search. However, this is not practical since it increases tuning time. To avoid this, we first randomly select a configuration from a search space of uniformly distributed, equally likely combinations of tuning parameters. This prevents the search space from exploding. The plugin requests for the energy consumption for the phase as well as the RTSs in each experiment. Additionally, the plugin collects PAPI hardware performance counters that are used to characterize the phases and perform clustering. Selecting the right metrics is crucial since this influences the clustering and ultimately the selection of optimal configurations. We selected 3 features for clustering. First, compute intensity. This is a good metric to determine the DVFS setting, since codes that have a high compute intensity have the possibility of reusing data in the cache and hence have fewer last level cache misses. We define compute intensity as the ratio of AVX calculation instructions to the L3 cache misses. This, however, is not the best metric to determine the uncore frequency setting, since the L1 and L2 caches are part of the core, while the L3 cache is part of the uncore. L2 cache misses have a direct effect on the uncore dynamic power consumption since they cause activity on the ring interconnect as well as in the L3 cache due to data movement. This means that if all the data were in L2, no performance trade-off is imposed. The final metric chosen was the number of conditional branch instructions, which represent a change in the control flow within a single phase. It should be noted that different events differ between microarchitectures and across different vendors, and we focus on optimizing the tuning framework for the Intel Haswell architecture. We use the features to perform clustering in this tuning step. First, we perform DESCAN. It's a well-known density-based clustering algorithm that groups points that are close together, resulting in high-density regions. It marks points lying in low-density regions as noise. It can detect clusters of arbitrary shapes and requires 2 parameters to cluster. First, min points. This refers to the minimum number of points that define a cluster. We set this parameter to 4, which means a cluster must contain at least 4 points. The second parameter is epsilon. This is the threshold or the maximum distance between any 2 points in order for them to belong to the same neighborhood. This is automatically determined using the elbow method. In the first clustering step, DESCAN ignores the similarities or associations between the noise points, which can be done using spectral clustering. This works in the similarity space instead of the original feature space and relies on the eigenstructure of a similarity matrix to partition similar points. Similarities between individual points can be specified using an affinity matrix that says that 2 vertices are connected if the similarity between them is larger than a certain threshold. We use the well-known Jordan-Weiss normalized spectral clustering algorithm to cluster the set of noise points into k different clusters. Here, we first form the affinity matrix as defined by this equation. The Dij term here refers to the radian distance between points I and j, and sigma is the connectivity or scaling parameters and controls the width of the neighborhood. For more technical details on the algorithm, please refer to our paper. Using the affinity matrix, the algorithm computes the normalized graph Laplacian matrix L. It then determines the k largest eigenvalues and forms a matrix X. Spectral clustering uses k-means as the final step to extract the clusters from the original data points, and k-means is used directly to cluster phases. When the natural clustering doesn't correspond to convex regions, it results in unsatisfactory clustering. Instead, eigenvectors of a Laplacian matrix are used to transform the low-dimensional points into a spectral mapping. To compute the number of clusters for k-means, we determine eigengaps between the eigenvalues of the normalized graph Laplacian. We then select the first point that produces the largest eigengap between the eigenvalues. Previous tuning step evaluates only a subset of the entire search space of tuning parameters. This means that in the best case, each phase in a cluster is executed with a different configuration. In the worst case, all the phases in the cluster are executed with the same configuration. This makes it difficult to select the best configuration for the cluster with a high confidence due to the fact that there are no other configurations for comparison. We implemented a new tuning step that evaluates each phase in a cluster with a configuration that has never been executed in that cluster. This uses a random search strategy based on a normal distribution. The basic idea is that certain configurations are attractors or repellers. Attractors are those that result in a lower normalized energy consumption than the energy threshold, and repellers result in a higher normalized energy consumption. The algorithm is as follows. We first compute the energy threshold as the average of the minimum and maximum normalized energy consumption values obtained for the phases of cluster C. We define the weight for each configuration X as a function of the influence of the attractor and the repeller configurations. So these two functions can be expanded as the function of the energy consumption as well as the Euclidean distances between the configuration X as well as an attractor or repeller configuration Y. So functions for the attractor and repeller represent the Gaussians for the attractors and repellers, and smaller values for sigma result in sharper or taller peaks, while larger values result in smoother and wider curves. We first compute the overall probability mass function for every possible configuration in the search space. Finally, for each phase in the cluster, the plugin uses the compute probability mass function to randomly select a configuration and evaluate in an experiment under the following conditions. First, no phase will be executed with a previously executed configuration. Second, the chosen configuration should be either close to the attractors or far from the repellers. And finally, if a previously executed configuration is selected, it is discarded and another configuration is selected. We illustrate the conditions using an example. Let's assume that the phases in cluster C were evaluated with 9 unique configurations, of which 5 are attractors and 4 are repellers. This figure shows a 3D surface contour plot for the final probabilities. It should be noted that we compute a discrete probability mass function, and hence the connecting lines in the surface plot do not indicate continuity. Attractor configurations have higher probabilities and thus they are colored in blue, while repellers are colored in red. We can also see prominent peaks for the strongest attractors. To satisfy the conditions, we set the probability of previously executed configurations to 0. Hence, here we see that previously executed configurations now have the probability of 0 and will never be selected again. In the last tuning step, the interface tuning plugin requests the Redux runtime library to switch to corresponding cluster-based configurations at the start of a new phase. For the RTSs, the configurations are switched to the RTS specific best configurations for the current cluster when the region enter event is called. This basically tries to verify the tuning success. If a phase was marked as a noise point in the cluster analysis step, it is executed using the default system configuration. The plugin finally outputs the savings resulting from static and dynamic tuning. We now present the results of the tuning plugin as well as static and dynamic savings for 2 real-world applications, Samoa and Indeed, evaluated on the Intel Haswell logs on the Technical University of Dresden's top 500 cluster towers located in Germany. The default core frequency of each CPU core is 2.5 GHz and the default uncore frequency is 3 GHz. Energy values were measured using RAPU and frequency switching was performed using the x86 ADAPT library. We tested 2 real-world applications, Samoa and Indeed. Samoa is a hybrid MPI OpenMP adaptive mesh refinement framework. It's written in Fortran and runs 1141 iterations of the simulation time loop. Indeed is an OpenMP application also written in Fortran and runs 154 iterations of the simulation loop. We evaluated both applications on a single node with 24 processes for Samoa and 12 threads for Indeed. Samoa stands for Space Filling Curves and Adaptive Measures for Oceanic and Other Applications. It performs the simulation of a tsunami wave propagation as well as 2-phase porous media flow. The simulation of a tsunami wave propagation is performed by solving a system of time-dependent partial differential equations called shallow water equations. The simulation first sets an initial state and then refines the grid incrementally. It applies a displacement to simulate the initial tsunami wave and finally executes the time-stepping loop on the generated grid, combined with adaptive mesh refinement in each iteration. The simulation domain, which is the ocean, is discretized with the Cartesian grid, and the unknowns of the PDE are placed at various grid elements such as grid cells, vertices, or edges. We evaluated a methodology using a maximum refinement level of 20 for a total of 120 iterations of the simulation loop. The figure on the left shows the trend for the compute intensity across the entire application execution. The figure on the right illustrates the final clustering obtained after performing DESCAN followed by spectral clustering. 4 clusters were produced. We can see that for clusters that lie in the region of low normalized compute intensity, low setting of CPU frequency is recommended and vice versa. A high amount of traffic entering the L2 cache is indicated by cluster 4, for which higher setting of the uncore frequency is beneficial. The table lists the RTS specific best configurations for the RTSs of Samoa for each cluster. The RTSs are identified by the call paths. As we can see, the cluster best configurations for the phases depicted in the previous slide are not necessarily the best configurations for the RTSs of the significant regions. The best configuration for the RTSs of the significant region, Euler traverse section, has a high setting for the CPU frequency and a low setting for the uncore frequency, except in the case of cluster 4. Thus, we can say that this region is compute bound for the phases belonging to clusters 1 to 3. Indeed, simulation involves a stationary workpiece and a number of tools with different geometries that move towards this workpiece. When there is a contact between the tool and the workpiece, adaptive mesh refinement is performed, where the number of finite element nodes increases between time steps. This also means that the computation cost increases with the rising number of elements. The simulation in Indeed consists of 3 loops: the time loop, contact loop, and equilibrium loop. But each iteration of the contact loop executes the innermost loop, which is the equilibrium loop. Evaluated a methodology using the input side for a steel benchmark for a total of 100 iterations of the simulation loop. The figure on the left shows the trend for the compute intensity for the entire application run. Here, the first phases are computationally very cheap, since there is no contact between the tools and the workpiece yet. The figure on the right illustrates the final clustering obtained after performing DESCAN followed by spectral clustering. 5 clusters were produced. Clusters in regions of low compute intensity benefit from a lower CPU frequency. For example, in cluster 5. The table presents the results of the significant region analysis and dynamism detection by redex DynDetect. As we can see, 5 significant regions were detected for Indeed. The region RES2 has 2 RTSs that can be identified by the call paths. We also observe that different best configurations for the RTSs of RES2 for the first cluster are obtained. Hence, we also exploit the interphase dynamism here. The table presents the static savings achieved for the phase as well as the RTSs and the dynamic savings for the RTSs in percentages for both Samoa and Indeed. Here, we observe static savings of 24% for Samoa and 10% for Indeed. The static and dynamic savings for the RTSs for both applications in columns 3 and 4 are in the range of 4 to 5%, while the dynamic savings for the RTSs with respect to the default system configuration shows much more promise, with an improvement of 9.25% for Samoa and 8.77% for Indeed. Systems require more than 50 megawatts of power to reach the exascale level. So far, existing tools generally rely on static tuning where a single frequency is set for the entire application run. This approach has the drawback of being too coarse-grained. Our proposed approach implements a fine-grained tuning methodology which selects the best configurations for both phases as well as RTSs by grouping similarly behaving phases, first using DESCAN followed by spectral clustering. We also perform search space optimization using a targeted search of the tuning parameters. For future improvements, we plan to compare the energy savings on newer Intel processors such as Skylake to leverage the new architectural implementations such as hardware power management. Additionally, we also plan to implement a runtime prediction library to predict the cluster IDs of all the phases that were not seen during design time analysis using a second order Markov chain. I thank you for your attention.